Hello everyone, I am Sujal Chavan, currently pursuing Electronics and Telecommunication Engineering from Vidyalankar Institute of Technology. Currently I am in third year, that is SEM 6, and studying a subject called Advanced VLSI. And our course instructor for the subject is Professor Akhil Masurkar sir. He is assistant professor and senior member of IEEE from Department of Electronics and Computer Science of Vidyalankar Institute of Technology. So I have made this PPT regarding an assignment. So the assignment was referring a research paper and making a PPT from that research paper. So the title of the research paper was Lightweight AES Design for IoT Applications Optimization in FPGA and ASIC with DFA Countermeasure Strategies. So the abstract was IoT devices require lightweight encryption due to limited processing power. AES is widely used but must be optimized for power and efficiency. The paper focuses on improving AES architecture in FPGA and ASIC hardware. It also examines differential fault analysis, that is DFA, attacks and countermeasures. So this paper explores lightweight AES designs optimized for IoT applications. Introduction. IoT devices are growing rapidly but face security risks due to limited power and memory. AES needs to be optimized for low power, small size and high efficiency. DFA attacks are a major threat to AES implementations. The study reviews past improvements and proposes enhancements for IoT applications. It also discusses various countermeasures to prevent these attacks while ensuring that security improvements do not overly burden IoT devices. The paper aims to guide future research on making AES encryptions both secure and efficient for IoT applications. Literature survey. Researchers have tried to optimize AES for IoT while balancing security and efficiency. Lightweight AES modifications help reduce power but introduce new risks. This paper proposes better architecture to enhance security while reducing resource usage. Methodology. The study optimizes lightweight AES, that is LWAES, for IoT, implemented on FPGA and ASIC for real-world applications. Key modifications include S-box, sub-bytes, shift rows, mix columns, add round key optimizations, DFA attack analysis, fault injection scenarios, rounds and positions are examined. Countermeasures, fault detection mechanisms, area efficiency, security performance. So the study also analyzes the vulnerability of AES implementations to differential fault analysis attacks, evaluating different fault injection scenarios, round and positions. To mitigate DFA threats, various fault detection mechanisms are explored, balancing security with minimal hardware overhead. The proposed designs are evaluated based on gate count, power consumptions, maximum frequency, and security performance to ensure their sustainability for resource-constrained IoT environments. So these are the block diagrams which shows a visual representation of AES encryption and its optimizations. Shows how data flows through different AES steps, and the third one highlights where modifications are applied. So these were the block diagrams which uh, which I have extracted from that standard IEEE research paper, and these were the results mentioned in the research paper, which summarizes DFA countermeasures are analyzed based on detection levels, methods, protections, positions, overhead cost, throughput performance. So the findings were some methods, example Hamming code, MCPL. These methods provides high security with minimal overhead, and the other methods like example hardware redundancy have high area overhead but offer strong protection. So this was the summary of the result obtained. Result discussion. The table summarizes various countermeasures for differential fault analysis detection in FPGA and ASIC implementations, highlighting their detection levels, methods, protection positions, overheads, and throughput degradation. It includes techniques such as duplication, self-test, CRC, and masking applied to components like registers, SBox, and key schedules. Overhead percentages vary significantly with hardware redundancy showing the highest area overhead, that is 86.5%, but no frequency or throughput degradation, while CRC exhibits high area 73.1%, that is, and frequency, that is 35.5% overheads. Some methods like MCPL and Hamming code maintain zero degradation, making them attractive options for lightweight AES implementations in IoT applications. So these were the results. So we jump onto the conclusion that it likely emphasizes the importance of optimizing AES implementations for resource constrained IoT devices while ensuring resistance against differential fault analysis attacks. The study evaluates various countermeasures in FPGA and ASIC environments, balancing security, hardware overhead, and performance. The findings suggest that lightweight DFA countermeasures such as masking techniques, error detection schemes, and redundancy-based approaches can effectively enhance AES security with minimal impact on area and throughput. Some methods like Hamming codes and MCPL show promising results by offering robust protection with negligible performance degradation. However, a trade-off exists between security strength and hardware efficiency, necessitating careful selection based on application needs. The research includes that integrating optimized DFA countermeasures into AES designs is crucial for securing IoT applications while maintaining efficiency. Future work may explore further optimizations, low power designs, and resistance against emerging attack vectors. So there were some merits of the research paper, and so the merits were a structured study covering both hardware and software aspects, The research paper explains real-world applications in medicines and biotechnology. The research paper provides a clear comparison of traditional versus modern imaging methods. So the demerits of the research paper were lack of real-time implementation examples. More discussion needed to be on challenges of using the softwares, could include a cost analysis and future improvements also. So here were the references which I took from the research paper.